Hello, this is my storyboard. This is my storyboard for a story I want to tell, introducing something that I think is very important. I have a theory of particle physics which I think will satisfy the majority of the problems that people are having in defining what our universe is like. First of all, this is me. My name is George Cerbola, and you can get me on email at cerbolaphysics@outlook.com, or you can just sign on to YouTube, put in my name, George Cerbola, that's S-I-R-B-O-L-A, and these videos will come up. Now, let's do this in an orderly fashion, okay? I know lots and lots of videos are on the YouTube with the theory of everything, theory of particle physics, theory of the universe. There's one difference with mine. Mine is based strictly on physical attributes. No games, no weird names, no strange things. Now, based on measurable physical attributes. That's the term I wrote down. And we're going to talk about mass, energy, and size of this, which is the primordial energy mass unit, which is what I am theorizing is the basic particle or unit of the whole universe. Going down the ladder of complexity, and that ladder will come up to, I've got a list that starts here with the elements and goes down into atoms, and then into protons, and then into quarks, and then it disappears. Well, I'm going to go way, way down that list and go down and create a new one. And the way I'm going to do it is I'm going to use the proton as the one to start with. The reason I picked the proton was because it is a measurable unit that we can work with today. Scientists are able to do all kinds of things with it, and this is one of them where they were doing the size. And we know its mass, and obviously if we know its mass, we know its energy. Well, it turns out that the proton has a mass of 938 million electron volts per c squared. Now, if you're going to talk about something that is 938 million, then that sounds big, but actually a proton is pretty darn small, and we'll get to the size in a minute. What I did was I took that size and I said, if I climb down the ladder of less and less complexity, what's the lowest number of complexity I can come up with? 1. Okay, that's a good number. There may be smaller, but that's the one I picked, and it's working out pretty darn good. So now if we have a particle, or a unit as I'm calling it, just to give it a name, of 1 electron volt per c squared, then what does that do to size? Well, if you do a little bit of manipulation and you say, hey, I've got 900 plus million of these in this little proton, and I've measured the proton to a size of 0.86 times 10 to the minus 15 meters, and my apologies to these guys because they found 2 different numbers, but their numbers were like 0.86 something and 0.87 something, and that's a problem for them. But for our purposes, it's okay. We're just going to set the stage for all the rest of the stuff. So by doing a little manipulation, it turns out that our little unit, the PEU, is about 1 times 10 to the minus 28 meters. That's a very small size. But at the areas that we're talking about, okay, so what? So it's small. Now, the next thing we got to come up with is energy. Well, that's an easy one. you just go to Einstein and say, Mr. Einstein, your equation, E equals mc squared, is a perfect one, because if I put the 1 eV per c squared in as the mass, then multiply it by c squared, the c squared disappears, and I have my energy. Energy is 1 electron volt. Well, that may not sound like it's important, but think about it for a minute. Here we have a particle who has a mass of 1 electron volt per c squared. That means you got to divide it by the velocity of light squared, and that c squared is, I'm not even going to give you the number because it's 10 to the something number, 6 at least. But that says that we have a particle, a unit, that has this much energy and this much mass. That's important because as we start accumulating these things to make up our quarks and our protons and our atoms, we're going to see where mass comes from. It means that we had mass, we started with the beginning, with the PEU already there, because energy and mass are the same thing. Now that takes us to the point where we're going to have to do something to say, well, if this is really the level of what we're talking about, then we're going to have to prove out with our little theoretical handy all the things that make up our universal processes. And what I'm going to do is go collect some things, and I'll be back. Here I am, I'm back. What I did was I collected some things to just be able to give you a demonstration of what we've been talking about. And what I just told you about is our little primordial energy mass unit, which is combined into what I'm calling packets, PEPs, primordial energy mass packets. And those packets are going to be in different sizes and different shapes. And let me explain what I'm talking about. If my little PEU is about this size, okay, and I take two of them, they become a packet. But let's talk about them on a little ball to show you what they are like. And what I've done is I've made this ball and I've marked it so that there's a north and a south. And the reason there's a north and a south is that little PEU, the unit, is a mass of unknown quantity, whatever it is, and it's rotating. And anything that's rotating, like this and the Earth, creates a field around it in which the positives repel and the positives and negatives attract. Like repel, unlike attract. If it's rotating and it's got a field around it, and you get another one that's rotating and it's in the same orientation, they're going to repel. Now, if they're not in the same orientation, if one in the north is on the bottom and the north is on the top on this one and the bottom on this one, when they come together, they're going to attract to each other. But just think of the various combinations that these could have in all the different ways. And I got some little charts out of Wikipedia that show the magnetic fields around the Earth, and there's no reason to suppose that the fields around these are any different. And if that's true, and I theorize it is, then these things will come together and they will attract and become, and depending on the number that are attracted, different PEPs. When you get way up this ladder, up to where we can measure things in quantities, they become things like an up quark, a down quark, a top and a bottom, and the colors. When they put photons into the Large Hadron Collider and smash them together, what they're trying to do is they're trying to get these things to come apart. Because if you've got a whole bunch of these together, hundreds of thousands of millions maybe even, then the more of them that are together, the stronger they're going to be. And depending on their alignment and combination, they're going to either be repelling or attracting. So that we can have just about anything you can think of. And I found these little balls that show little bumps on it all the way around. And assuming that this is a bunch of PEUs accumulating into a PEP, and if this is a down quark, and this is an up quark, it takes two of these and one of these to make a proton. And it takes a proton and a bunch of these around it, the PEUs maybe some other form of the PEPs, and we got a helium atom. And then from there on, anything can happen. Now, I'm showing you solid balls. That's interesting. I'm showing you soft balls. That's interesting. But that isn't the way it really is. It's more like these washcloths. When you take two of them and they're rotating, and this one's rotating, whether they're north or south, when they come together, they're going to be interfacing, and they're going to be connected. So that when they really come together, really tight, they're going to be the same size they were. One of them was. So we can accumulate these things in tremendous amounts to make all kinds of strange things. What kinds of strange things? Well, if you go to the fundamental particles and interactions, the standard model that they have, all of these descriptions, each of these things in here is composed of my PEPs in different combinations and permutations. And the more of them there are, the stronger they are together. All right. They also account for decay, and we'll talk about that. As a matter of fact, let me take the list here and just sort of skim down it and tell you all the different things that I have tried to insert my PEPs into, and they seem to fit. Okay? Talk about an atom. Talk about all the elements in the periodic table. There it is right there. That's just more of the same of these. Okay? Now, if you want to go and discuss what the background radiation is that they've been measuring, this will help you. If you sit down and think about it for a minute, think about how if the universe is made up of 96% of the things we can't measure that are below the visibility range, and they're in these different packets that I'm talking about, then there's that whole background radiation thing that just pops up in your mind. Then you talk about the Big Bang. How did that happen? Well, I'm a little confused about what the Big Bang was, because everybody thinks of it like there's a little nothing sitting there and then it blows up. Well, that isn't what happened, obviously. But if you think about it physically, when I just showed you these two little things and they come together, and two of them coming together and they're still the same size as one of them, you could keep adding millions of these together. Now, what happens is that little tiny amount of mass characteristic that each of them has and the energy combined start adding up, and this thing starts building up and building up. Well, if the big universe we have sitting out here, this megaverse, is full of it, and somehow these things start collecting and they start accumulating, and they get very, 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 very energetic and hot, they reach a threshold. And at that threshold, they just decide, well, like happens in the supernovas, boom, everything blows apart. That's the beginning of our universe, okay? Now, we can go from there. Let's go to the other end. Let's go to a black hole. If you hear what's been going on about the black holes, we theorized them and we found them, but we're finding out now that maybe they're not really black. Well, a while back when I was going through theories prior to this one, I had some other ideas before this that weren't quite as far back in the ladder. I said that black holes were not just taking things in, they were also spitting them out. Because all the frequencies of light that we use to look at them showed something spewing out. So what is a black hole? It's a recycling bin of our universe. Okay? Now we got to talk about dark energy and dark matter. Well, that's almost obvious. Down below our visibility, there are PEPs. Let me see, where's my PEPs? Right here. Of different sizes, different complexity, that make up what we're calling dark energy and dark matter. And because of their configurations and combinations, they'll do exactly what everybody is measuring as the weight of the universe, the mass of the universe, the energy of the universe. You know, then we talk about fields around the Earth. We talk about space curvature. This is a perfect example of what space curvature is. If the Earth is a mass of my PEPs, and there are PEPs all around it at lesser and lesser complexity and density, out to infinity practically. There is no infinity, I know, but that's beside the point. Then that's just space curvature, because anything that comes into that field, moving at all, is going to curve right into the Earth, and it's going to be like, ooh, there's a curvature. Okay? We can even use it to define the Higgs field. We keep talking about a field out there, but we don't know what we're talking about. Well, the field is right there. There is a field. It's the field that these generate around them. Okay? We talk about the megaverse, and then we talk about the polarity. Then we talk about the singularity, which was the Big Bang that we talked about. And we talk about the strong force, and we talk about wave-particle duality. That's another one. Now, we keep talking about waves, and we just get lost when we start defining it. I know that they did the slit test to show wave duality. Well, the existence of my PEUs and PEPs creates an environment where the waves will work. The wave-particle duality is right there, because as you're transmitting photon of light and it goes through the slit, it's packed with the PEPs all through everything, and it makes waves in those PEPs, and they will interact in a spherical form, and we will get the lines. So there's a concise description of what I'm trying to sell. Now, when I say sell, I'm trying to get some people to take a look at this and say, okay, what are the experiments we have to do, and what are the tests we have to do, and what's the rest of the theorizing we have to do to make this thing, well, whatever it's going to become. So what I'm going to do is I'm going to leave it right there, and then I'm going to take my time and do some more theorizing and putting together some more videos that takes each of the things on my list, and that list is like, there's about 30 things on here, and I'd like to go down the list and write a description of how the PEUs and PEPs will satisfy what we know about these things. Not what we theorize, but what we know about these things. Then we can talk about other things later on. So with that, let me repeat where you can get in touch with me. CibolaPhysics@outlook.com, or on YouTube, type my name in, George Cibola, and my videos will pop up. There were about 5 or 6 of them in there, but I took them all off, and I put this one together so that I could get, I hope, some particle physicists and cosmologists to take a look at this and say, gee, you know, there's an idea there. And because I really believe that this is what is at the basis of our universe.